was established last year with generous contributions, which I'm sure some of you in the audience established a permanent lectureship in honor of our first founding director of the Center for Computational Medicine and Bioinformatics, Professor Gil Omenn. And this is the second annual Omenn Lectureship. So we're thrilled that you're here. We're glad that you found us here in CVC and not in our regular location over at the Danto Auditorium in the Omenn Atrium. The Bioinformatics graduate program was started in 1999 when Professor Burns was here somewhere and Phil Andrews walked the paperwork over to the Rackham School and started the graduate program. And we matriculated our first student into bioinformatics, PhD student, in 2001. And in 2005, Gil is founding director and me as founding associate director went on this journey together to start the Center for Computational Medicine and Bioinformatics, which launched very well and started to engage folks in interdisciplinary collaborative research and big centers and the like, with a focus on bioinformatics and translational bioinformatics. And we built that up, and we're honored to launch the Department of Computational Medicine and Bioinformatics in 2012. And so we have now some 13 core faculty and about 13 or 14 affiliated faculty. And so as I was telling Professor Kohane, when we call a faculty meeting, 25 people show up. And it's really wonderful to see. And, the faculty, in bioinformatics and computational biology have just been flourishing here. And with Andrew and Chuck and Yule, we're now working on the clinical informatics counterpart, the academic clinical informatics counterpart. So informatics is building here, and the guy who was really responsible for seeing this at Michigan, without a doubt, was Professor Omenn, and we're just absolutely thrilled that this lectureship is happening today, and we are honored to have Professor Zach Kohane from Harvard Medical School, MD, PhD, and really one of the founders of the field of biomedical informatics. We're absolutely thrilled that Zach is here. I've known Zach since we were both assistant professors. We obtained our first big contracts together from the National Library of Medicine, from the Next Generation Internet Program, him for the Spin Pathology Informatics Network that Dr. Belize back there had something to do with, and us for the Visible Human Project that launched that across the country. So we've been friends ever since, and it's been a great friendship. And so without further ado, I will turn this over to Professor Omenn, who will introduce our second annual Omenn Lectureship. And thank you very much, guys. We're thrilled that this is just launched so well. And proof is by how much interest there is. Gil?
Great. Thank you all for coming. Thank you, Brian, for getting the lectureship launched and getting today's session launched. It is a special treat to welcome Zach Kohane here to Michigan. I hope most of you were here last year when Lee Hood gave the inaugural lecture. And next year, speaker will be David E. Shaw. So mark your calendars. We don't think we've put out the date yet, but it will be terrific. Zach was born in Geneva, Switzerland, and graduated from the renowned International Baccalaureate program there. Came to the United States to do his collegiate work at Brown. Just told him that our brand new president, Mark Schlissel, just arrived from Brown after a distinguished career as an MD, PhD, starting at Princeton, Hopkins, Whitehead, and then Berkeley. And he's interested in everything across the campus. Of course, now he's got to put a lot of attention on football. Zach is really a pioneer in this field in which we're all engaged. He is the model for bridging from basic science and computational science all the way through clinical and public health informatics. The I2B2 platform, which I'm sure we'll hear about, is developed by him and his team jointly with Partners Healthcare, and has been adopted now at dozens of places around the country, including here at Michigan, and in the Transmart scheme that Brian and others of us are deeply engaged in developing together with Zach and some of his key colleagues at Harvard and Ken Pient and others at Hopkins and multiple important pharmaceutical and data companies. Zach is the Henderson Professor of Pediatrics and Health Sciences and Technology, Director of the Center for Biomedical Informatics, also the Director or Co-Director of the Francis A. Countway Library of Medicine at Harvard Medical School. I had the privilege for the second cycle of chairing the Harvard Overseers Review of the Harvard Medical School. One of the more distinctive features is this Center for Biomedical Informatics. For me, it was particularly interesting to learn more about what Zach and his colleagues have been doing or hoping to do, because, as you just heard, most of you participated, we started with a center concept here and have matured it into an academic department, which has given us considerable further momentum. And we're very proud of what we're doing here. We still look to leadership from other places, and that's why this kind of a lecture is so valuable. I also had the privilege for the Dean of Harvard Medical School in chairing the review of the proposal to develop that center into a department. And I can tell you my colleagues Dan Masis and Russ Altman and I were so enthusiastic about this that the dean got more than he bargained for. Basically, we told him that Zach's proposal was too timid. And much more was needed and much more should be done and much more surely could be done under his leadership at Harvard and for our field globally. Zach, welcome.
Well, I'm very honored to be here today, especially in a lecture that came up still. I know that this part of the discussion bores all the young people, but remember what they always say, be nice to the people on your way up, because you're going to meet them on the way down. And so I have to say that in very unexpected ways, both Gil and Brian have been extremely influential in my own career by example and also by creating recognition of biomedical informatics as a discipline. And so I'll tell you something, I can't say it's in confidence in view of how many people there are here in this room, but it's very likely that in about a month and a half, the Dean of Medical School is going to announce a department in biomedical informatics at Harvard Medical School, and that's in large part because of Gil's leadership. So I'm quite indebted, and a lot of us are very, very thankful in that regard. So I find that I fall asleep in my own lectures if I don't spice it up a bit. So two warnings. One is, in the middle of this talk, I'm going to ask you a question, and I'm not going to move on until you answer it, and we'll embarrass you by showing you. So there's a big question that's going to be asked. Keep awake. And if you're not awake, I'll wake you up. And second of all is, what's the point of this talk? The point of this talk is to say, you know, medicine is a very, very fine discipline, but it's actually quite appalling the state in which it currently is. I was reminded of this when I was in the emergency room with my mom, who's in her late 80s, just half a year ago. I was at the Brigham, and they know who I am, and so they try to show me, you know, that they're smart and taking good care of my mom. And they came and told me she had diplopia, double vision, and she was unsteady on her feet. And the guy was telling me exactly where he thought the stroke might be. And it's been, I'm trained as a pediatric endocrinologist. I have a PhD in computer science, but I'm definitely not an adult medicine or a doc or a neurologist. And so I said, I don't know if what he said actually sounded quite right. I didn't quite remember. So I just typed into Google for symptoms. And sure enough, there's a list. The top item was not the one that he had told me. And sure enough, when the MRI came back, it was what Google had told me. So I think much more broadly, we're not sufficiently data-driven, and I'm going to try to show it to you from both ends. Acquiring the data, understanding the data, and then making the data useful for patients. I just want to remind you of the context. We live in a healthcare system that has many, many ways of getting paid. Until very recently, there was only 5% electronic health records for most across all doctors in the United States. But after bribing doctors to the tune of about $44,000 per doctor, there's been a much wider uptake of electronic health records, and that's closer to about 40 to 50%. And there's now much newer models of healthcare delivery. I think it's very telling that in the middle of the heart of darkness, right in Longwood medical area, surrounded by all the Harvard hospitals except for MGH, there's a Minute Clinic run by CVS that is where you go to, where if you want your kid to have a quick ear check or a shot immunization. And so things are not going to stay the same forever. And then there's a threat or promise of accountable care. And certainly, even before things are changing, people are maneuvering to reposition themselves. And in the context of flat NIH funding, academic health centers are looking for new models of reimbursement. And I think it's also telling that there was a large multi-million-dollar deal that was signed between Regeneron, a pharmaceutical company, and Geisinger, where essentially the entire electronic health record data and their patient samples were made a commingled property so that they can sequence hundreds of thousands of individuals and share the IP. And I think we're going to see more and not less of this happening in the near future. So that's the context. And I want to make sure that you understand that we're going to be talking about both the afferent and the efferent parts of healthcare informatics, getting the data from the environment, from the patient, and thinking about it, doing something with it, and then pushing it out to actually squeeze a muscle or do something that actually improves the healthcare of the patient or a population. So let's start with the afferent nerve. So I've long been inspired by Jean-Marie Charcot, who was a physician in Paris who worked at a large Salpêtrière hospital. He did something which many of his colleagues poo-pooed. He systematically looked at every single patient. And this was mostly a patient for psychotic individuals or for individuals with a variety of neuropsychiatric diseases and neurological diseases. And by virtue of systematizing what he saw in the hospital, he actually defined a whole new set of diseases, which created a real impetus in neurological science that had not happened in the 200 years before, and actually exceeded much of which happened 50 years afterwards. And so I was inspired, can we actually use the byproducts of healthcare delivery, the observational byproducts of healthcare delivery, and the material products to actually advance healthcare delivery. But I've taken a very expansive view of this, and I hope to convince you in the time that we have left that you should too. This is a diagram that we published in the Journal of the American Medical Association just a couple of months ago. And in it, we show you the landscape of healthcare data. And shown in blue are the data that come out of the healthcare system and out of claims data. But there is a much larger, and some of it is structured and some of it is unstructured. But there's a much larger source of data that comes from 23andMe, Ancestry.com, fitness club memberships, and just the social web, which many of us tend to poo-poo because it doesn't look like the officious medical data that we are used to. But I'm going to try to persuade you that it's at least as useful, given the fact that most of us will spend much less than 1% of our lives in the healthcare system. So Gil alluded to something called I2B2. That was the name of a grant, Informatics for Integrating Biology and the Bedside. And this grant just simply said, let's automate what Jean-Marie Charcot had done at Salpêtrière. Let's create software to pull data out of the electronic health record and push it into analytic frameworks so we can understand what's happening in the healthcare system, both for genomic research, for quality improvement, for public health, and for accountable care. Because as I always like to say, you can't have accountable care if you can't count. So this software was so needed, it was such an unmet need that although this actually looks like a very sparse graph, there's over 80 academic health centers in the United States which have implemented this system, which is free and open source. But as also I like to say, it's free and open source like it's free like a pony, because you have to feed it and you have to clean up after it. And so these academic health centers will spend $1 million, $2 million or more to actually implement it, but it's worth it because of what they can do with it. And there's about 20 more sites in Europe, and a lot of them are in the Transmart version of I2B2, which Gil and Brian have actually taken the lead in implementing. And so, what can it do? Well, by looking at the entire health record, we can look beyond claims data, which after all are just the billing data. We can actually look into the textual record and through natural language processing, extract exactly what the patients have. So this shows in just one healthcare system, Partners. Now Partners sounds like a big system because it's the Harvard hospitals. It's actually small. It's 4 million patients if you include a single visit. It's 2 million patients if you require 2 visits or more. And so this shows if you take these patients and you define through natural language processing, what are the patients who have asthma or major depression, and then which ones come back to the system, and you can obtain their discarded samples. You see that we can obtain on the order per week, on the order of 600 samples per week. Rheumatoid arthritis, about 200 samples per week. Something even as rare as Huntington's disease, 3 or 4 samples per week. Now here's the point. These are very large numbers per week, and the incremental cost is $18, including DNA extraction. Now, contrast that with the price of a DNA extracted sample to NIH, averages between $1,000 and $3,000. To pharma, $10,000 to $50,000. So this is a disruptive technology in that allows you to do these population studies at much lower cost in much shorter time. And of course, time is money for a pharma. And the biggest evidence of that was an episode where one of the biotechs came to me after we published this in Genome Research, and they said, we want to study 5,000 patients with this specific disease entity. How much would it cost? And like sort of like Dr. Evil, I said, $1 million. And I immediately had seller's remorse because they instantly agreed to my price. And so I knew I'd way underbid it. But the point was, it really makes you able to do studies in a year that would have otherwise taken you millions of dollars and years. And this slide is to show that not only does it do it cheaper and faster, it does it well. So here's a genome-wide study, a genome-wide association study where we're looking at rheumatoid arthritis. And on the y-axis is the odds ratio of the risk for rheumatoid arthritis. And what you see is after you get past the HLA complex, a bunch of SNPs shown with the blue dots that were done in a multi-million-dollar, multi-year study using automatically phenotyped patients using natural language processing. We redid the study with the red dots, and if you know what genome-wide association studies look like, that's very good reproducibility. And so we're able to reproduce the same findings at 1% of the cost in about 8% of the time. Moreover, whereas the previous studies were all done in individuals of European extraction, we were able to repeat the study in those who are historically underrepresented in these studies, namely individuals from underrepresented minorities. And because why? Because in academic health centers, they're overrepresented because of the fact that Hispanic Americans and African Americans tend to use academic health centers as primary care sources. And so we're able to rerun these studies literally at a press of a button and publish, in this case, the fact that they had very similar profiles to that of Caucasian Americans. So opportunity is always helpful to take advantage of it. And so there's something called the CTSA, Clinical Translational Science Award. And Harvard wanted to compete for it, so they came to me, Lee Nadler came up to me and said, hey, we have to show that Harvard really works together, because no one believes that Harvard works together. And he's right, because there's an axiom, which you'll now know as Zach's axiom, is the distance between two hospitals is inversely proportional to the amount of mutual loathing. And so you can imagine when you have hospitals that are all together in the Harvard medical area, they don't get along at all. And so when I proposed to Lee that we use the fact that all the Harvard hospitals had I2B2 instances, these clinically extracted databases, but I proposed that we create a distributed query system that would do real-time queries across all these hospitals. I literally had senior vice presidents yelling at me saying, "How dare you do this?" But in the end, we prevailed. We came up with a solid governance policy. We came up with solid IRB mutual reliance agreements so that any investigator, including junior faculty, including postdocs, could actually go to the system and access the 10 billion facts across the 6 million patients across these hospitals. And that was interesting, but the question was, could they do anything with it? Could they find rare things, or could they find common things with small effects? And so I was gratified when one of my narcissistic Google alerts was triggered that someone had cited the paper which I described that distributed query system. And I said, what had they written about? Well, they had written a paper in Nature about a disease that kills women in their third trimester, peripartum cardiomyopathy. And these were a group of young investigators at the Beth Israel. But they had a hypothesis about angiogenic imbalance that looked pretty good. But when they approached the editors of leading journals, they said they did not have enough to validate their study. So using this distributed query system that we call Shrine, they were able to get 4 handfuls of patients across the 6 million patients and able to publish this without ever asking us, as was appropriate. And they were able to publish the result. So think about this. It would have never been possible for them either practically to go through 6 million patients or politically to go across 4 hospitals, and yet we enabled them to do this in a month. That too is a disruptive acceleration in the ability to do research. Here's another kind of disruption. This is a diagram that shows on the x-axis time going from 1997 to 2006. And in the middle of it, you see a big mountain. Now, this is a mountain that if you flew a Malaysian airliner into and it disappeared, you'd get very worried. If you sent 2 Malaysian airliners into it, you get really, really worried. But if you get through 1,000 airliners into it, say, why is no one paying attention? And so this is what happened. These are our 2 best hospitals in Boston. And this was a 17% increase in heart attacks. And until we did the analysis, no one was aware that we had a 17% increase in heart attacks. What kind of healthcare system flies 1,000 wide-bodied jets full of patients into heart attacks and never understands that it happened? But it wasn't only happening with us. Why is that? So what was happening here? Biax in, biax off. And the peak is when the first real big public announcements were. But it's very important to know that the first papers, including through our colleague Garrett Fitzgerald, showing that there was a problem, came out much earlier. There was only a few places, but it was notable, and we know that Kaiser Permanente took it off formulary, probably because of cost issues, but also because of safety issues. The rest of us flew 1,000 airliners into that cloud. So not only was there, so internalize that for a second. Not only did we not know there was this huge increase, we did it. What is that saying about healthcare? You know, you'd be giving me a standing ovation maybe if I told you that we decreased heart attacks by 5%. This was a 17% increase, and we didn't even know about it. That is not what I think of, what I used to think of when I was a kid, thinking that I'd go to the doctor and they'd use all the information from all their encounters to do the right thing. And just lest you think that this was a great, as we say in medicine, retrospectoscope exercise, looking after the fact, in the middle of the controversy around Vandia and oral hypoglycemia, we were able to show, again, a 50% increase shown by the red line in Avandia relative to Actos, a drug in the same class. And it's still very controversial, and people are arguing back and forth because there's billions of dollars at stake. But nonetheless, we were able to show it before the FDA called it. In fact, they cited our paper as a example. And here's the ironic thing. We were not a public health group. We were not a pharmacoepi group. We were just a bunch of biomedical informaticians looking at data. And no matter how we adjusted the data, we could not get rid of this increased risk from Avandia. And yet, all the other hospitals kept on doing it. And here's the biggest problem. All this pharmacovigilance, we're still not doing it. We do M&M rounds. We don't look at the data and see, are we doing as well as we were with our patients last year as this year? What's the overall burden of disease? Where is it shifting? We don't look at that. We have no air traffic control for this. And if you look at the data, it's like shooting fish in a barrel. Again, this is a work that one of our faculty, Griffin Weber, did. And it just shows the following. On the x-axis is your aid. On the y-axis is just a number of facts that we know about you. These facts can be anything. It could be the number of labs, a lab value, it can be a diagnosis. And it just shows that there's a weird nonlinear relationship between the number of facts and likelihood of death in the following 3 years. And it shows this is far better than any actuarial prediction. Just without even knowing your diagnosis, I can tell who has 80% survival, 70% survival, just on fact count and age. And you can see those who have a lot of facts and those who have few facts are the ones that are most at risk. And both of it has to do with access to healthcare, the nature of the diseases. But the point is, we don't use any of this data to actually manage our patients. We don't crowdsource our doctors. Here is what looks like a very noisy but important relationship. It's for one lab value, white blood count. And it shows on the y-axis how many days until the white blood count test is repeated. On the x-axis, what is the white blood count value? And what you see, of course, is with very high white blood counts, it's repeated very, very fast because it's either an infection or a cancer. Also, low white counts, you repeat fast. Now, this is very noisy, and you can see very large error bars. But we were able to use this data and we do this same time to repeat across hundreds of lab values. And we're able to predict with 75% accuracy, based on how bad the labs are on presentation, how many days the patient is going to be in the hospital. And we're just using the crowdsourced value of lab values. We're not using what a lab control center typically does, 400 or 500 samples and say, what's normal, what's 2 standard deviations. This is getting a smooth function across the entire range of practice. And this just shows that we can actually capture context beautifully. These are those same time to repeat for different age groups. So this is defining normality across multiple pediatric sites. Here's another type of data that is available trivially to us, and we don't take advantage of it. Here's one patient that at the middle of this strange radar screen is coming into the healthcare system. And as I've taken all their ICD-9 diagnoses, all their diagnoses out of the emergency room and clumped them into these categories. And you see this one patient, as you approach the present, which is the circumference of that circle, they have these multiple diagnoses in those areas I show. I just want you to think about for 3 seconds, what is the diagnosis of this patient? What? That's pretty good. People at University of Michigan are smart because the modal answer is Munchausen's, which for those of you who are not doctors means they're basically lying to get a variety of medical intention. So that's very cynical doctors, maybe Harvard. But the point is we're able to detect domestic abuse through, on average, 2 years before the healthcare system is aware of it, and up to 6 years. Just by looking at this was an algorithm just trained on all the visits to all the emergency rooms across Massachusetts. And we're able to predict domestic abuse much ahead of doctors. Again, what kind of system it is where a doctor can't look back and see all that pattern? You actually don't need a naive Bayes algorithm, which we had. But the point is, in a 30-minute ER visit, no doctor's going to look back and get that picture. So why not actually have a app that actually would summarize that and say, there's high risk here. We'll get to why there's no apps in a second. So switching gears for a second, I've been doing some studies of autism, and I can't discuss it too much just because of time. But one of the studies I did was a gene expression study on peripheral blood. A little bit of crazy idea doing peripheral blood gene expression. And these were the pathways that came up based on the genes that were differentially expressed between patients who had autism versus controls. And what we found, fortunately, what we found, sorry, there we go. What we found is some pathways which made a lot of sense. Neurotrophin signaling pathway and long-term potentiation, which is involved in laying down a memory. These were differentially expressed. I was thrilled, but then my annoying graduate students pointed out that there were a number of immunological pathways that were also differentially expressed. They said, "What?" And they said, "Zach, what do you expect? You're really just seeing immunological features in white blood cells." And I said to them, "Well, that's a problem." But then I thought about it further. It was, in fact, different in the cases versus controls. And at that point, I looked further into literature. I mean, if you go to neurobiology at Harvard and in many other places, and you talk about autism, you'll hear about disorder of activity-dependent learning, disorders of the synapse. But then if you go into another literature, you'll see, for example, in pathology samples of children who've had sudden death, let's say from a car accident, you'll see that they're compared to controls. Their microglia, which are the macrophages in the brain, are massively upregulated. There's on proteomic assays, a very large innate immunity and chemokine signal in the spinal fluid as well. And in the peripheral blood, there's also differential response to a variety of immunological stimuli. Furthermore, if you look at entire countries, like Denmark, if you have a mother who has rheumatoid arthritis, or a father who has type 1 diabetes, you're much more likely to have autism. Or if your mother has an infection during pregnancy, much more likely to have autism. And so, you heard that I'm the director of the library, so the following impulse happens naturally to me. I asked myself, how does the literature look like if you look at all the papers that look at autism and synaptic function, denoted by N, autism and the genetics of synaptic function, denoted by N, and autism and the genetics of the immunological function, noted by I. And as you can see, it's a not very overlapping set. Worse yet, the literature that they cite is very, very separate. And what that tells us is something that happens very broadly in medicine, and that I think if we went systematically using the tools of bioinformatics, would happen less often, which is that you have these silos, even within a given discipline, which never talk to one another, don't show up at the same conferences, don't cite one another, and because of that, really don't serve the patient well. And let me give you an example of that. So back in 2012, using that I2B2 network, because I have enabled these academic health centers to have the software free to their sites and supported them, it was not very difficult to create a network of 8 sites to have the largest comorbidity study ever of autism, on the order of about 14,000 patients. And we were able to do this analysis in about a month. And so this was the largest comorbidity study ever. And one woman by the name of Sonali Doshi, who had just graduated from MIT the year before, she then spent 2 years doing the work that I'm about to describe, among other things. And now she's a faculty member at the School of Engineering and Applied Sciences at Harvard. But what she did is very simple. She took, for each one of those 14,000 patients, she took each 6-month block of their lives, since we had at least 15 years on each of these patients. And for each one of those 6-month blocks said, what other medical conditions or comorbidities do each one of those patients have? And we created what's called a bit vector, or in simple English, a 1 or a 0. A 1 if you have that comorbidity, a 0 if you don't, in that 6-month block. And then she marched it out through all 15 years. And then what she did was cluster the patients. So doing literally the same cluster analysis you do for gene expression circa 1999, she did it using the morbidity profiles of these patients. And what we saw are patients who were similar, clustering together, just as genes sharing the same functional program clustered together. And here's what we found. So we found one group that had 80% epilepsy. Now, the background rate for epilepsy in autism is about 20%, but there was a subgroup who had 80%. There was another subgroup who had a lot of infections, viral and chlamydial infections, and not shown here because it's off scale, inflammatory bowel disease. And then we had a third group that didn't have a lot of seizures, didn't have a lot of infections, but had a lot of neuropsychiatric disease. ADHD, anxiety, not shown here, schizophrenia, because it's a lower frequency, although many times higher than the background. So here's the point. These are 3 different diseases. They don't look like one another. And if I were to try to do a association study today, a genetic association study on heart failure, and I lumped into the heart failure all the valve problems, all the viral myocarditis, all the atherosclerotic disease, and all the structural genetic disease into a case control study, you'd laugh at me because you'd say, Zach, you're mixing up a very heterogeneous disease. But that's exactly what we're doing with autism and many other diseases. And what we're using here is deeper phenotyping, which we could not afford before. It's actually cheap to do genomics, but it takes a lot of time to do phenotyping if you require a medical student or a research assistant to read the record. But if you can use a computer to do natural language processing, all of a sudden you can read millions of records in days. And by the way, the most interesting and valuable part of this for me was something that never happened to me in my life before, which is a number of families, when I published this, wrote to me desperately thanking me for having acknowledged what they had never had acknowledged by the doctor, that there were these constellations of findings, inflammatory bowel disease, infections, and autism in one case, which had always been seen as just random events. Of course, if you see 1,000 patients, which is a large cohort of autism kids in your developmental medicine center, you only see maybe 10 with inflammatory bowel disease. And so you may not remember, it may not rise to your level of attention. But across these populations, all these subtypes become much, much clearer, much more evident. This is just a slide to show that this is amazingly reproducible across academic health centers. For instance, this is Wake Forest versus Children's Boston. Different doctors, different patients, different health cases. How am I doing for time? Oh, good. All right. So I told you that we should not poo-poo non-traditional forms of data. So this is work that one of our faculty, John Brownstein, has done. And when he first showed this, a lot of faculty thought he was wasting his time, and I'll let you judge for yourself whether he's wasting his time or not. But again, this is part of the rubric. We're still on the Efferent arm of biomedical informatics. So this is the traditional model of getting data for population health. You go from the public all the way to regulatory agencies through this number of middlemen. And I grew up in Switzerland, as you heard, and so I assumed that at the WHO, World Health Organization, there would be a DEFCON 5 set of screens showing the world burden of disease, and that somehow they were tracking it all. Of course, that's not true. And in order to be able to take advantage of what's available, John has actually taken all those components of that chain and actually flattened them conservatively with the following kinds of effects. So he takes all this babble of social media and has turned it into public health monitoring that is far cheaper and far more responsive than traditional public health monitoring. So, for example, in this article he wrote in the New England Journal, he showed how they were able to track a multitude of diseases, including H1N1, from the index cases in Mexico all the way throughout the world by just reading automatically through natural language processing the news feeds throughout the world. And he actually does this for literally hundreds of diseases, hundreds of infectious agents, and parses data in several languages from Chinese, Arabic, Spanish, Russian, English, and French, for starters. He does this every hour. This is the public health servant that never sleeps. And by the way, the WHO and the CDC actually use this as one of the primary modes of actually measuring public health impact. And so it generates 2,000 alerts per day, precisely placed in 10,000 locations. And of course, for instance, you can look at his site now under healthmap.org and see the unfortunate distribution of Ebola and the very scary predictions of what it's going to look like under various assumptions of infection control, even the most optimistic. It's very bad, by the way. And so this has had very big impact. This gets distributed to a variety of health authorities, and they're being used systematically. And this is an example of the kind of parsing he's doing in these multiple languages across these different sources. And again, the alternative is not public health workers. It's nothing, because it's only a small number of public health workers doing the kind of data coverage. Okay. So I think that's just summarizing what I told you before. And this is an example of how, in fact, they're able to track H1N1 through the news in this fashion directly from Mexico City. How about foodborne illnesses? So the CDC reports 1,000 foodborne illnesses in the United States every year. HealthMap reports 10,000 such illnesses. What you can say is that just random noise. Well, this is what it looks like. And this is the data sources like Yelp, things that we would not consider as normal substrates for study. And yet, the distribution of causes from these non-conventional data sources look just like the CDC. And he has developed something called Medwatcher Social that uses the social web to actually look for adverse events of a variety of different drugs. And it's quite challenging, but it's quite effective. So these are the kinds of tokens that they're looking for in the social web stream. And, lost appetite. And nonetheless, they're able to categorize these very effectively into different adverse event categories systematically, and the FDA is now using this systematically to track adverse events. I think one last non-conventional source of data. You've heard of genome-wide association studies. Let me show you an environmental-wide association study. This was done by one of our faculty who we stole from one of my former students at Stanford, Atul Butte. And what this is, if you on a conventional GWAS, what you see across the bottom are the chromosomes, and the negative log odds ratio of the p-value of a SNP is shown on the y-axis. Here, instead of the chromosomes, you have biochemicals, and those that rise above this environmental-wide von Peroni correction are ones that, in this case, are implicated in diabetes. And so he used a data set out of NHANES data set that has been obtained for decades now, and was able to reproduce this toxin as having a high odds ratio for diabetes. And this vitamin metabolite is actually being protective of type 2 diabetes. So again, we should remind ourselves that genomics is exciting, but for most common diseases, it only represents 50% of the disease burden at best. And so if we don't actually measure these other sources of that kind of variation, we will fail. Now to start wrapping up, I would like to look at the efferent nerve of biomedical informatics. So, what time is it? All right. So back about 4 years ago, I held a clinical bioinformatics summit at Harvard to ask ourselves the question, what would it take to do clinical grade whole genome sequencing? And we assembled a number of luminaries, both genomics, informatics, lab testing, regulatory. And it was an interesting conference, but quickly it devolved into the most boring topic possible, standards and interoperability. When I realized I wanted to shoot myself, I asked the attendees, can we actually do something interesting? Let's actually see if we can actually do this for real. And so I went to the CEO of Children's Hospital and said, can I have $25,000 as a prize, and will you give me free license to go and find families in Children's Hospital who have a child who's very sick that we expect to have a genetic condition? And they found, and she said yes, and I found 3 families, and we got pro bono sequencing, and both whole genome and whole exome sequencing done by 2 companies. And then we put the data out there, and 30 teams competed internationally. It was quite remarkable. And within a couple months, they had actually come up with some answers. And even more interestingly, 7 out of the teams had converged on the same answers. In fact, the leading teams converged on the same answers. Interestingly, by the way, as an aside, many of the teams that did not win were also using the exact same analytic pipeline, but we're just using it with much less creativity. We do not have on the same team the clinical expertise as well as the bioinformatics expertise, as well as the understanding of what genomic quality control is about. And that made the difference. And this is the large cast of characters that all participated in that clarity challenge. But here's the real issue. This child had gone for 12 years without being diagnosed. And he had something called centronuclear myopathy, which sounds like it's a fancy diagnosis, but all it is the label for what the picture looks like of his muscle under the microscope. It's a purely symptomological diagnosis, and not an etiological diagnosis, just like is the case for most medicine. And so he'd gone for many, many years without a diagnosis. And this is the birthday cake his mom gave him when we gave him this diagnosis. And what was really quite interesting is, apart from the fact that it was quite explanatory of disease and, in fact, explanatory of a heart problem the mother had, but 2 of the hospitals where he had been seen previously had not made the diagnosis. And yet, somehow, when we had focused this multidisciplinary set of teams on this challenge, they came up with a diagnosis. And that tells you that the way we practice medicine at these very excellent hospitals is broken, because somehow the way genetics is practiced does not take advantage of the full knowledge base that is required to effectively analyze these full data sets. So I'd like to think, when you hear the word precision medicine a lot, and I'd like to just give you the following definition of precision medicine from the point of view of biomedical informatics, but I think it should be the definition that doctors use, which is what's the probability of having a disease given the findings, and it's precise to the extent that you have very small error bars around that probability measure. But that's not the way most doctors think about disease. In fact, let me give you a question. And this is where I warned you. I'm going to ask you a question now, and you're going to show me how smart or not the fine people in Michigan are. So let's take a disease, zombie disease, and if there's a zombie disease has a prevalence of 1 in 1,000. And this is the question. It has a false positive rate of 5%. So 5% of the time, it incorrectly diagnoses you as a zombie. What is the chance that if we say everything that we know about Brian is explained by the fact that he has a positive test? He's positive for zombie disease by virtue of this test. So 1 in 1,000, it's perfectly sensitive, no false negatives. So if Brian is positive for zombie disease by this test, how likely is he to be a zombie? So I'm going to make it easier. How many of you think it's 95% chance, hands up, that Brian is a zombie? Just based on this test. There's other reasons why he might be a zombie. 90%. 80%. 70%. At some point, you're going to have to raise your hands. 60%. 50%. I see some hands going up. 40%. He's positive for this test. 30%. 20%. A lot of hands going up. 10%. More hands going up. 5%. 2%. Impressive. All right, 0%. All right. So this question was asked, this very question was asked 30 years ago to Harvard Medical graduates. We asked the question again 30 years later of experts, medical students, residents, fellows. And this is what we found. This is close to 100%. That means they thought that this 95% or higher likelihood of being a zombie, and those are down close to 0. Now, just in case you're feeling left out, I want to quickly work this out for you. If it's 1 in 1,000, okay, and then in 1,000 patients, there's 1 true positive. You're with me so far? Okay. So since there's no false negatives, it's a perfectly sensitive test, you're going to get that 1 patient. But if it's 5% specific, it's 5% false positive, it'll be 50 individuals who have a false positive test of zombie disease. So you'll have 51 positives, and only 1 of them will actually be a zombie. So that's why can we really hope for doctors to use screening tests effectively? Is there any wonder that we've done that, especially when cash additionally muddles the picture, why we're ripping out prostates of men based on their PSAs? We just heard Mary Claire King, a very, very fine woman, just say that we should be doing BRCA tests on all women. She's very, very smart, but I don't think she's appreciating this issue. We actually published this in JAMA Internal Medicine, a couple of relationship with math. I'm actually going to skip by the following fact. So something that we thought of as being a completely Mendelian disease, hypertrophic cardiomyopathy. There are a number of variants that in this recent study were shown to have prevalences about 1%. And we looked at it and said, how could that be? They were looking at a big exomic data set coming out of the National Heart Lung Blood Institute called the SB data set. And we looked at it more closely. And what we found out was in this SB data set, the frequency of this 1 in 500 disease. This disease only happens in 1 in 500 individuals. This disease for 4 of the top SNPs had 5% or greater, up to 20% frequency in African Americans. Because African Americans come from a gene pool that precedes the bottleneck when we came out of Africa. There's a lot more variation. So these variants are not causal. 20% of African Americans don't have HCM. And yet, based on these variants, many athletes have been taken off the court, have had defibrillators implanted, have had their whole family screened because we don't understand these basic mathematical relationships. So when we're talking about an efferent arm, there's a big problem, and that problem is our ability to do probabilistic math. And the answer is not necessarily to teach everybody how to be a Bayesian, although it'd be nice, that's my fantasy. But the real answer might be to actually have decision support that really works. Have automated decision support that really works. But what's it going to take to do automated decision that really works? So I was quite amused to see this on the web. I found this slide, this picture on the web. It says, doctors and residents working with patients at the JF Clinic in St. Louis. Where the hell are the patients? And the problem is, this is so true. It's so true. Anybody who has an MD knows that in the generations that I've gone through, we went through from writing admittedly illegible notes, then spending time with the patient, just sitting behind a glass pane on the keyboard, never seeing the patient, and just, that's us. And has this been caused by? It's been caused by process automation, the thing that I had totally hoped would happen. That was a $44,000 per physician bribe. And why is that? Why is it so bad? Look how happy I got. Oh, by the way, I mean, literally in the emergency room, the girls and boys used to have 3 or 4 hours of sleep at night. The patient load hasn't changed, but those 3 and 4 hours are now in data entry. Here's why it is. It's the reason why this is because these systems. Yeah. Okay. Sorry. These systems that brings knowledge to the point of care, which have names like Epic or Cerner or Greenway and others, are systems that are state of the art for 1980s. And I remember, so there's something called Office of National Coordinator that Chuck used to be part of. And I remember there was a guy called Farzad, and Farzad was director, and I just saw him. I was at a fancy investment banking conference in Napa Valley, and I saw among the architects of managed care were there, Bob Kocher and Farzad. And I recalled in front of the audience an interesting quote I saw in the New York Times from Farzad. So that he was at one point head of the office that funneled all those dollars to healthcare, IT. And he said, because he was implementing a lot of IT systems in New York. And in the New York Times, he said, healthcare IT is really complicated. It's not like an iPhone. First of all, I think iPhone's not that simple. But then immediately, I did what I do best, which is I wrote an article which said, essentially in the New England Journal, why can't healthcare IT be more like the iPhone? Because when I have an app that doesn't take good photographs, take another photo app. If I have a to-do app I don't like, I get another to-do app. If I take my electronic calculator system and I don't like the order entry, you know what I have to replace? The CIO and the CFO. Because it's a multi-10, 30, 40, 50, $100 million investment. And these things are written on purpose as big monolithic giants so that you can't actually create any new app that implements some of these insights that I told you about when I was talking about the Efferent limb of healthcare data. And to give Farzad and his company credit, and I think he was sure to point it out in front of that audience last week, he got a $50 million grant to actually show how you would create apps on top of electronic health records. We call it the smart platform. And basically, it's a way of creating software that's a thin layer of dynamic HTML that takes data sources, such as electronic health records, presents the data in a container that multiple apps can run in. And so, for example, we took this contest result that was in Wired, where they came up with a beautiful rendition of what a cardiac risk screen should look like for doctors or for patients. The only problem here, this was published in Wired. It was a PDF. So we took that PDF and in our smart system, 1 week with a developer, we had it implemented across a personal health record, across an electronic health record, across a data repository. And furthermore, the same smart system now works against genomic data. So you can have genomic data coming out of the electronic health record and clinical data coming out of the EHR and actually have decision support for genomic data that is currently not available. I was talking to people at Geisinger. They've been told by Epic 2 years ago that the genomic data was coming a year ahead of time, 2 years ago. They still don't have it. It's not going to come anytime soon. So this whole genomic revolution is happening with our IT unable to deliver on that promise. But using this technique, we can. Now, I was very happy with our technological development, but I was very concerned and cynical that we would not actually succeed because the electronic health record vendors, just like Microsoft when it ruled the desktop, really don't want to let anybody in at all into their system. So I was very, very surprised this year at this conference that I never go to, but it's huge, called Health Information Management Systems. And it's where all the electronic health record vendors present. And there were multiple booths where different vendors and different provider sites were showing their data being displayed using our smart system. Because it's finally giving the ability to show these new apps, new growth chart apps, new genomic apps, new domestic abuse detector apps on your platform and sharing across these platforms. Because even a Cerner or Epic, even if they're phenomenally good and have thousands of developers, that is a tiny fraction of the amount of smart developers that are worldwide. Apple and then Android discovered that in the app storm that they unleashed by creating that API for their various platforms. And what we're hoping we've done is open up that API, a standard API for these vendors so that you and others can start creating apps that even a large team of developers working for that monolithic system will not be able to think of. So my question to you is, if we're not going to have this, how do we get here? How do we get to the point where we can look at our patients in their blue face and actually have a discussion where we actually take full advantage of the patient-clinician relationship, where technology is on the side, doesn't get in the way, where we're actually being supportive in our decision-making, where we are truly laying on the hands, and that, in fact, we're bringing the best and latest of our thinking, but the collective thinking of the medical establishment to bear. And so the questions I have for you in closing are not so much a question, well, it starts with a statement. I don't think we should wait for the medical system to fix itself. Right now, most of healthcare can't seem to find its way past ICD-10, the new billing codes, or meaningful use. It's not trying to answer the questions that I brought to you today. So who's going to drive this? I think it's, if not anywhere else, it's going to be biomedical informatics. Do those quants, those of us, need special certification? And I'm not talking about MDs, because it may be that this will come from non-MD direction. I don't know. Or do we need to create fast-track medical education for individuals who might not necessarily practice, but understand the medical system and will bring quantitative reasoning to bear? Are we willing to worry about patient safety? We think, we say we care, but I just showed you that huge mountain of heart attacks. I am sure that even in this august institution, we're doing things to patients en masse that we're not even aware of. And it's a certain amount of complacency that should be done. I mean, guess what? We're doing it to ourselves, to our parents, to our children. And so when are we going to decide that we're going to actually take this data and start, we have to start somewhere and morbidity and mortality rounds were started way before surgeons ever had a p-value around their findings, but they were aware of what's going on, at least in their operating room. Can we become aware of what's going on in our healthcare system? So how do we affect the effector arm? I know it's very boring, it's very applied, it's workflow, but are we interested? Are we interested, or are we going to say this is something that the CIO has to worry about and we don't have to worry about? I can't tell you how many department chairs I've heard of medicine or pediatrics say, oh, our electronic health record system is terrible, it prevents me this or that. How much involvement did they have in any decision making on the electronic health record? Some, I mean, most, not at all. And for a large subset of them, they were offered many opportunities to opine, but they didn't think it was important. So my question to you is, what will it take for clinical leaders to pay as much attention to data workflow automation as reimbursement rates? Those are the real questions. And if we don't take that seriously, we're not going to succeed. We've got to answer that question. And should this not be sorry for the N, a medical priority? With that, I'll thank you and take any questions. Yes. Identify yourself so I know which enemy you are. Give me one example of a specific disease. All right. Well, first of all, on the one hand, in addition to your registry, you should be completely on top of all your outcomes, even if they don't look like outcomes, from your electronic process. And I know it's really crummy data, but I'd run natural language processing, and I'd have someone in charge of being on top of that. Second, there are actually some best practices that you can track. Whatever electronic health record system you have, I'd say, can I either work with a vendor, unlikely, or can I create apps on top of it that actually implement the guidelines? So we're in a fantastic era in cancer, where for the first time, some of these molecularly defined subtypes are making a huge difference. I can point you to a site in Nashville at Vanderbilt where they have actually provided decision support. None of those rules actually are implemented in an electronic health record. You could be the first cancer center that would take those rules about if you have this variant, this is what you do, and actually implement in that system. Could be way ahead. And the short answer is it doesn't take that much to do it. Let me give you a quick example. So it sucks to be old, but one of the good things about being old is a lot of the junior people are your former students. So the CIO at Children's Hospital is one of my former students. And I said, Dan, what can we do? What's been a problem? It turns out something very simple. In a pediatric hospital, it's important to know what centile your blood pressure is, systolic and diastolic. Because just like height, 100 centimeters means nothing. Depends on your age, right? So the same is true of blood pressure. So in the endocrine program, the cardiology program, the lipid program, and the renal program, knowing what blood pressure, what your centile for blood pressure is actually very important in determining treatment, especially in the nephrology program. And they've been asking for 3 years for Cerner to implement some system to do this. So I said, Dan, let's put on top of Cerner a smart app. And after 2 months of politics and 1 month of implementation, I still see patients a little bit. I was blindsided in a good way that all of a sudden I saw on my menu in the Cerner system this thing that said blood pressure centiles, and then it popped up a lovely graphic with the patient's centiles historically and currently, and I could see where it was red and green. And that happened. It was not hard. This is not hard. It just takes leadership. The technology is not hard. A lot of CMIOs hate my talk, so it's okay. Yeah. I think that's extremely well put. So let me answer this in a couple ways. First, let me answer it constructively, and then I'll answer it defensively. So no, constructively first. So constructively, absolutely. Epic has announced that. Cerner did it first just because they're losing market share to Epic, so they had to do it first because they were getting their lunch eaten. And I think you'll see more and more vendors, because it's really hard to be in 2014 and not have an API that others can build on. Now, I think it's really important to take them up on that challenge, because I think it's grudging. And Dvorak crapped all over this idea 3 years ago, their CSO, but now he gets it because there's demand. And I think that the way to really test it is in twofold. One is to actually build apps. And incidentally, I'll just prove your point. I was at CHOP, and they told me that it's actually scary that when you are Epic certified, you actually get full access to all the underpinnings of the system, including keyboard combinations that can automatically zap all the underlying data, which is an interesting architecture. But in any case, they do not find it as difficult at all to build a smart API on top of it. So I think the short answer is the academic health centers first need to lead by actually building apps and creating the marketplace. And the best outcome would be if they would collaborate across vendors so that they should actually allow reimplementation with minimal work across the different platforms. So I think the short answer is, the constructive answer is, if you're an oncologist, you say, I'm going to demonstrate this with my Epic app implementation, and then I'm going to get my other cancer leaders around the country and say, are we going to adapt this app? Are we going to do more apps? And actually lead innovation from that side. And you know, people forget it, but things like Epic, underneath it is mumps, right? Where did mumps came from? What's the M in mumps from? From Massachusetts General. And because it was Octo Barnett, who never made a penny on it, who actually developed the language that 30 or 40 years ago actually is still underlying Epic. Probably much longer than you'd ever hoped or feared that language would last. But in any case, so the short answer is a constructive approach is what it takes, but it needs public leadership. You have to go out and say, we're going to do this, and join with your peers. If you're not going to do it, then it's my job to remind people what we're not doing, that Epic and Cerner can't actually do all this. They're too busy they're not going to be ready to do the genomic decision support or a lot of the safety stuff. And we have to create those frameworks on top of their system using the existing APIs. Now, the defensive part is, until we started really rattling the cage about this, and people were very upset with our original New England Journal article, until we started rattling the cage, there was zero interest and a lot of pushback. And if we contributed anything, maybe the Smart Fire API will take off or not. I think what we contributed by saying it can be done. There's nothing so mysterious that you can't actually create all this functional ecosystem on top of API. So I do hope that the way you net out what I just said is, by all means. But if I come back in 2 years and you haven't done any apps, I'll say, what the hell was that? You just let it's not so much showing up epic. It's showing that as academic health centers, we can lead for our patients, applying the best of what we know should be happening with patients on top of these very large systems. Yes? Is Titan. 100%. I think it's a great point, and I want you to reference the following article forevermore. In 2006, with Russ Altman and Dan Macy's, I wrote a paper entitled The Incidentalome, a Threat to Genomic Medicine. So the incidentalome, I've said, is bigger than any ohm, bigger than the genome, bigger than the proteome. So the incidentalome is going to be huge. And I can give you lots of great stories like that. And genetic background makes a big difference. So for example, hemochromatosis. 80% of individuals with hemochromatosis in the hereditary hemochromatosis clinic will have mutations in a gene called HFE. But in Kaiser Permanente, the Scripps Institute genotyped 40,000 individuals, consecutive individuals for those mutations. And they found 151 who were homozygous for one of those mutations, just as they had predicted. But only 1 out of the 151 had any clinical, biochemical, or family evidence of hemochromatosis. Genetic background matters, which is why the BRCA1 issue is big. And furthermore, I was lucky enough to get a grant for the Coordinating Center for the Undiagnosed Disease Network. And what we're doing is we're getting patients applying, they get their genome sequence, they get phenotyped. But I'm going to get to your point in a second, which is we're going to come up with a genetic diagnosis. But guess what? That's only the beginning of the story. In the end, to actually prove it, you need functional validation of it, to actually know that that is, you may disagree with that, but there are many, many mutations that look like loss of function that do not cause the disease. And so there are about to be many RFAs out for the Undiagnosed Disease Network for functional validation studies, because in the end, that's what has to be done, because otherwise you'll have false positives. So short answer is, you're right.
We thank you for a very engaging and important lecture. I can tell you, Zach writes well as speaks well, and he's got a huge bibliography. If you go to PubMed, you'll find a lot of other material you might find similarly very interesting and useful. So I want to invite everybody now to the poster session outside and the reception. Please talk with Zach directly. He's very approachable. And we thank you very much for this splendid afternoon.